Good day, everyone. I am Chandler M. Manlongat, and together with my thesis partner, Mr. Redemptor C. Lictaoa Jr., under the supervision of Dr. Kristopher Ray S. Pamintuan, today we will going to present our study entitled Compartmentalization Studies of a 3D printed plant microbial fuel cell with water lettuce. All throughout our presentation, we provide here an outline that consists of 4 parts, including the introduction, methodology, results and discussion, and finally the conclusion. Starting with the introduction, the persistent and rapid increase in population and continuous industrialization has led to sustainable and clean energy demands. This pressure creates a pathway to establishing renewable energy in the hope of tying down the world's reliance on conventional sources of energy, mainly on fossil fuels. One technology supporting agricultural cultivation and concurrent bioelectricity generation is plant microbial fuel cell. PMFCs are a type of bioelectrochemical systems that are capable of producing power from plant rhizodeposition. What it does is it capitalizes the interaction of plant and electrochemically active bacteria to transform chemical energy to electrical energy. It is also known as a modified version of conventional microbial fuel cell. However, what makes PMFC unique is that it includes plants in the anode proximity to fuel the entire bioreactor. As promising as it sounds, achieving stable and high power densities is a challenge for the development of PMFCs. This is due to the various internal resistances such as activation, ohmic, and concentration losses it encounters in the course of its operation.
Stacking and compartmentalization procedures were the more prominent solutions to the power issues. Stacking PMFCs involved connecting several devices in either parallel or series connections. Parallel stacking resulted in additive voltage output, while series connected PMFC had their voltage output averaged. Compartmentalization involves modifying the surface areas of the electrodes to increase power generation. Normally, the cathode surface area ratio is modified as this is the location for the rate limiting step of the redox reaction. Increasing the cathodic surface area provided positive results in studies involving both MFC and PMFC. An optimum ratio of 4:1 cathode to anode surface area was reported. The compartmentalized PMFC was constructed using 3D printing technology, an accessible way to print new design of PMFC aside from those constructed from conventional electrodes. Investigations into aquatic PMFCs also strengthened their viability in agricultural applications.
The objectives of the study is to determine the power generation of tubular 3D printed aquatic PMC using water vessels as a plan to construct a new viable design structure and construction method for aquatic PMFCs. Compartmentalization analysis was also done to determine how the surface area of electrodes will affect the power generation of the PMFC. Technology. The design of our PMFC caters an aquatic environment, and it is constructed in a floating arrangement. The one that holds the entire PMFC system is a 20-liter plastic container. This container is enough to carry the lake water substrate obtained in Laguna de Bay in Taguig City. The model plant used in this study is water lettuce sourced in Pagsisihan Creek in Parañaque City, an aquatic plant and scientifically known as Pistia stratiotes. This aquatic plant is famous for its lenient growing, which is advantageous for the experiment mainly because it offers minimal monitoring at the same time accessibility. To give you an idea about the design of our PMFC assembly, shown in this slide is a figure displaying our entire PMFC assembly in the actual fabricated structure. The design of our 3D printed PMC components is centered from a tubular configuration, which grants the transfer of charged ions in a radial manner. There are 3 major components in our 3D printed PMFC: the anode, cathode, and separator. All these 3 major components is uniquely designed in a 3D modeling software called Autodesk Fusion 360. The anode component is the site where organic compounds are oxidized with a population of electrochemically active bacteria present in the substrate. Shown here is the oxidation reaction that is taking place in the anode section. Instead of conventional and more fragile rods, the material used for constructing the anode is a conductive polylactic filament from Protoplasta. Moving on to the cathode. Cathode is the electrode component where the reduction of protons, electrons, and oxygen to form water happens. The reduction reaction in the cathode is also listed in this slide. The same with the anode, the material utilized for 3D printing the cathode is a conductive polylactic filament. The separator is a component that semi-permeably divides the anode and cathode chamber. Unlike the anode and cathode, the material used for the separator is a non-conductive polylactic filament. The actual photo of our PMFC is shown in this slide. Since the entire PMFC system is constructed in an aquatic environment, a floating material was used. The design of floating material can hold up to 4 model plants which surrounds and enclose the PMFC at the center. Each surface of electrodes are integrated with worm-shaft gear fin-type spiral thread design. Its primary purpose is to increase and vary the surface area of each electrode. The entire experimental procedure for measurement and monitoring is shown in this slide. The experimentation initiates with a 15 days acclimation period, followed by a 1-day polarization test, and ultimately a 10 days rapid voltage measurement for compartmentalization. In the acclimation period, a 15 days of waiting is allotted. This is necessary to give way for the settlement of biofilm and ensure that there will be stable and repeatable readings throughout the experiment. A polarization test was initiated after the acclimation period. This test was a prerequisite to compartmentalization to determine the maximum power of the PMFC registered at the optimum resistance. This is done by connecting external resistance of 1000 to 2 million ohm to each PMFC system. It is important to take note that the optimum resistance measured will be the base load for the rapid voltage measurement in compartmentalization. Compartmentalization, on the other hand, is divided into two parts, anode and cathode limiting. The anode limiting is when the surface area of the anode is held constant while increasing the surface area of the cathode from 1:1 to 7:1 cathode to anode ratio, while the condition for cathode limiting is the reverse of anode limiting. The surface area ratio parameter of electrode is shown in table 1 and 2. These parameters were achieved by adjusting the number of fin patterns on the surface of the relevant electrode to reach a surface area higher than its plane surface counterpart. By virtue of the Inspect tool feature of Fusion 360, the equivalent surface area for each electrode ratio is determined. Using a digital multimeter, the data gathering for compartmentalization was taken thrice daily for 10 days, from 9 a.m., 12 p.m., and 3 p.m. Some of the important equations used for processing the raw data is listed as follows for current, power, power density, and current density. In compartmentalization study, the response from the two experiments is the basis of the interpretation of what electrode configuration predominantly influences the gain for optimal power of the PMFC. For results and discussion, the resulting polarization and power curve for anode limiting, cathode limiting are shown in these two figures. From the conducted polarization test, it was observed that the measured values of voltage correlate directly with the amount of external resistance applied. This observation was noted to be parallel to the statements of Ohm's law, as a voltage is analogous to the resistance. Conversely, according to Semyon et al. 2020, a polarization curve presents the working voltage of PMFC as a function of the current density. This curve provides a useful information for the characterization of the chemistry and dynamics of PMFC operation. It displays various operating regimes of the PMC such as region of activation, ohmic, and concentration losses. In the generated polarization curve, activation losses were found to be significant at the beginning of the polarization. This regime persists at low current densities and large values with external resistance where the measured voltage drastically drops. As stated by Belvisi et al. 2012, the steep decline was due to the incurred loss during the redox reaction at the electrode. It was also observed that as the value of external resistance was reduced, the voltage decreased linearly with current density. The linear decrease of voltage is known to be the effect of ohmic losses. These ohmic losses were due to the resistance that was being set by the distance of electrodes sustaining such losses. Consequently, at high current density values, the voltage is found to approach zero. This regime accounts for concentration losses due to the effect of mass transfer. Another useful information was interpreted from the graph of voltage and current density. The curve generated is analogous to voltage and current density curve of a generator and battery, although the resulting trend is linearly decreasing, and the battery in the generator has a trend of logarithmic decreasing. It can be observed that it rests between that of the trend of the generator and battery. This provides us a valuable interpretation that the design of a PMFC has a tendency to act as a generator and battery at the same time. When it comes to the power curve, a power curve presents the power as a function of the current density. The power curve is very useful in determining the point of maximum power transfer in PMFCs. The polarization result shows that the 7:1 cathode to anode surface area ratio from anode limiting system records the highest maximum power density at 39.39 microwatts per meter squared. This was when 51,000 ohms of external resistance was connected.
The second part of the results and discussion deals with the data from the voltage measurements to establish the power generation analysis of each PMFC. The raw data from the 10-day voltage measurement was converted to average power and power density and then was graphed against the surface ratio values in Figure 6. Figure 6a shows the power data for the anode limiting systems. The 7:1 ratio garnered the highest power generation and power density at 0.17 microwatts and 36.9 microwatts per meter squared, respectively. Furthermore, a proportional relationship was observed between the increase in anodic surface area and power generation. This improvement in power generation is brought about by the increase in cathodic active sites, which helped speed up the rate limiting step in the redox reaction. The coefficient of variation was used as the percentage error bars to illustrate how the day-to-day voltage fluctuations affect the trend of increasing power generation. The variation on the 7:1 ratio is significantly higher than the rest, but is still the highest power generator, even accounting for its lower limit. Other PMFC studies report a similar proportional relationship between cathodic surface area and power generation. A 4:1 surface area ratio is reported to be optimum in a terrestrial tubular PMFC. Studies in microbial fuel cells using winery wastewater and a sediment type microbial fuel cell was also reported to have similar result from the increased cathodic surface area. The sediment MFC utilizes an aquatic medium similar to the current study and is reported to have an optimum surface area of 1.33 is to 1. Figure 6b displays the power generation results from the cathode limiting PMFC. The highest power generation at 0.10 microwatts belongs to the 1:1 ratio, while the 1:3 ratio at 7.4746 microwatts per square meter achieves the highest power density. The cathode limiting systems has no clear trend as the surface area ratio increases. The decreasing trend in power density is only due to the increased anodic surface area, which is the denominator in power density calculations. Variation in voltage are also high on all cathode limiting PMFC. A two-tailed independent t-test assuming an equal variance at alpha equals 0.05 was done on each pair of time periods in all surface area ratios from both configurations. There is no significant difference between the 9 am and noon values, but both are significantly different from the 3 p.m. value. This is consistent in all datasets except the 1:7 ratio, where all datasets do not significantly differ. These are the main findings of the study. The anode limiting systems improved power generation as the cathodic surface area was increased, but there was no clear relationship in increased anodic surface area. The 7:1 ratio PMFC has the highest average power and power density at 0.7 microwatts and 36.9 microwatts per square meter. It also has the highest maximum power density at 39.39 microwatts per square meter with an optimum load or internal resistance of 51k ohms. Large variations were observed in both day-to-day and between individual voltage measurements per time period of a given day. The 7:1 ratio PMFC has a higher level of variation compared to other anode limiting systems, or cathode limiting systems have similarly high level of variations. Using t-test analysis, the 3 p.m. voltage measurements were found to be significantly different from the 12 p.m. and 9 a.m. measurements, except in the 1:7 PMFC, where there were no significant difference in all time period measurements.